Hello, friends. My name is Will, and welcome to AI Ethics, part one of four. Part one of four. We are, of course, like 3 minutes before the hour, so we will just hang out until it's actually time to start. And I'm going to just double check to make sure that I am sending the bits to all the right places. Okay, I'm doing Twitch. We're doing YouTube. Did we do one time I streamed to LinkedIn, which I don't even know what that looks like on LinkedIn, but it was kind of unhinged. We are young business professionals here, and we send our stream to LinkedIn. But welcome. It's good to have you here. My name is Will. I will give myself a full intro when we're actually getting going, but I'm super psyched that you're here. Oh my goodness, Fancy Appleby, welcome back. Good to see you. Okay, yes, I will put on the flower crown. It's not really Global Hack Week until I throw on the flower crown, in my opinion. But welcome. Yes, I have to actually. I don't know what other streamers do, but well, I guess it's easy because most times, most Global Hack Weeks, like the one that is the AI one is the one that I'm running. But this time, all of them are the AI one, or at least lots of them are the AI one. And so yeah, there's less brand recognition for the Will stream. Wombo Combo, welcome. I will say, let's see, to get things going, let me know in the chat the most recent beverage you had or are having. I am right now double fisting some water and some Diet Coke. I feel like that's sort of like it's defense and attack. Drinking the water to keep me alive, drinking the Diet Coke to talk faster. I don't know. That's not actually a thing that I need to do. I need to censor myself. Welcome. About the 70th time I've said welcome. Fancy Appleby is consuming some water and Sprite. I love the water soda combo. The duality of man, apparently. So we are doing practical AI ethics in 5 minutes. There's going to be a lot of talking. We're going to do a lot of talking today. We're definitely going to write some code. We're probably going to implement our sort of first baby AI algorithm for this track today. And yeah, we're going to talk about how our algorithms can be evil and how to try to make them not evil. And it's going to be a great time. I think this is probably the stream that I have been most excited for like the past, year maybe. So I'm looking forward to it. Okay, so we are at 7 p.m. 7 p.m. Seattle Standard Time. I don't know what time it is where you live. Pashind, maybe that's how I'm pronouncing it. Welcome to the stream. Good to see you. So yes, my name is Will. I am a software engineer at Google, where I am actually recently, I've gotten involved in AI fairness testing, which will become relevant later. I am also a coach in Major League Hacking. I am a coffee addict. We're going to be doing a coffee live stream on Thursday, I think, so definitely tune in for that. What else am I? I am getting my pilot's license. That's a big update out of my world, is I am learning how to fly a plane, which is very exciting. Great question for Bashine. I don't know much about AI. Will I be a fit for this session? And I'm going to say the answer is yes. So there are a couple of things going on in this session. One is the fact that, or in this track really, one is the fact that I often feel like when we talk about machine learning, we dive all into the, here's how to code this thing up, and we spend very little time talking about what is the impact of this thing on other people, right? The other half of that is I think when we do talk about ethics in AI, we get very theoretical and very philosophical, and we don't actually talk about, hey, here's actually how to program an AI model or a machine learning model to be less biased or to be less unfair or to harm people less. And so those are basically the two pillars for me of this course is I do want to talk about sort of the ethical implications of AI, but I also actually want to do things hands-on. And so we will try to take it sort of step by step, and you should, even as long as you have some programming experience, if you have no programming experience at all, it will be, I will say, a fast learning curve. You can still stick around, and I would love for you to stick around. But if you have some exposure to programming at all, especially Python, that is kind of what we're going to be diving into. Fancy Appleby asked, what plane am I flying? So I am training mostly in, I don't know how familiar folks are with the world of aviation. Oh, you called it. Yes, it is. Oh, I've already messed up all of my windows. Here we go. Let's see. I'm going to pull up some photos of a Cessna 172. So Fancy Appleby guessed. Wait, Fancy Appleby, are you also a pilot? Do you have a pilot's license? That's super cool if so. So this is the kind of plane that I am flying a lot. Also a 152, which looks pretty similar. It's just a little bit smaller. Yeah, it kind of looks the same. But we're so good at getting on tangents. Fun fact, I'm colorblind, and so they make you jump through a lot of hoops if you are colorblind and want to be a pilot. It's kind of a nightmare. But yeah, I just got a flight sim set up, so I'm playing with that. Okay, back to the main course here. So we're doing AI ethics, and the goal is to both be think about these ethical ramifications, but also actually be hands-on and look at what it looks like to actually code something up. I'm also going to try to do better about dismissing comments when I show them. So also, before we get too deep, definitely check in for this session so you get points or whatever. Also, stick around until the end because I'm doing this classic thing where if you stick around to the end, I give you a feedback form and you get to vote on something silly that I'm doing or that I'm going to do. And I solicit recommendations. So in the past, I have face painted myself. I have dyed my hair. I have gotten a tattoo. It was temporary, but I did get a tattoo. And you get to vote on what dumb thing I do. But this time, I thought we'd try something different. And the way we're going to do it is everybody is going to submit a prompt. And I'm going to feed that prompt to ChatGPT, and whatever ChatGPT says, then that will be the thing that we vote on is which of these responses from ChatGPT should I actually do. Let's see. Shuta Shaksena, I shouldn't try to say the whole username, asked, how do I check in? So I just dropped a link in the chat that starts with organize.mlh.io. I think I can probably highlight it. Yeah, just go to that link, and that is how you can check in. All right, right on. What else? So yeah, stick around. I'll drop that link. And also, if you submit the feedback forms for all of the first 3 sessions, we'll raffle off some swag as well. So stick around, have a good time. And I think on that note, we're 5 minutes after the hour. Let's really just dive into things. Okay, so we're going to do some table setting. Actually, in the chat, let me know, have you attended any other AI or machine learning streams during this Global Hack Week or previous Global Hack Weeks? Have you had any exposure to any of those things? Because if everyone's yes, I know about machine learning, I just took another session, I will play to that. Otherwise, we will be very sort of basic and rudimentary. But so let me know in the comments sort of where you're at. Actually, we'll play this game. On a scale of 1 or of 0 to 2, give me a 0 if you literally have never heard the word machine learning. Give me a 1 if you are kind of familiar, have maybe dabbled, and then give me a 2 if you are currently a machine learning researcher. Give me one of those scores in the chat. Okay, cool. That's perfect. So we will walk through kind of at a gentle pace. We won't rush. Also, if I am ever talking too fast, let me know in the chat to slow down. So what is machine learning? So anytime we want to get a computer to do a task for us, if the computer gets better and better at that task as we give it more experience in the form of data, that is machine learning. So it's whenever a computer does something and it gets better when you give it more data, right? Which this definition actually means that there are lots of things that are machine learning, right? Technically, just I don't know, finding an average, that is technically machine learning because your computer gets better at identifying the true average of something the more data you give it, right? To make this concrete, here's just a random example. We could use data from the sale of houses in the past. So we could record, oh, that house over there sold for $100,000 and that house over there sold for $200,000. and we could build a model to predict what a current house should sell for or would sell for. And if we only have a few past examples of what these houses sold for, our model isn't going to be very good, right? But if we add a lot of examples, it should get better. So obviously, lots of headlines about large models like ChatGPT and DALL-E, et cetera, et cetera. Generally speaking, those are run on like a percentage of the whole internet, right? And so they have a frick ton of data behind them, which is one of the reasons they're able to do their task so well. So when we're talking about machine learning, okay, thank you all for dropping in your ratings. We got 1s and 5s, or sorry, 1s and 0.5s, a 1.5. Okay, fancy Applebee, actually. Wait, what are you up to? Let me know. But so it sounds like we're all in a pretty good place. Like no one's like, I've never heard this word before, but we're all sort of like, we're all beginners. And honestly, the machine learning in this course is not going to be super, super difficult. But the thinking really rigorously about like what fairness means, that's going to be kind of the part that we're going to go harder on, if that makes sense. So we kind of know what machine learning is. It's anytime our computer gets better at a task when we give it more data, right? And generally we talk about 3 big kinds of machine learning. We usually talk about supervised learning, unsupervised learning, and reinforcement learning. These are sort of like the big 3 we throw out there. There are other like subcategories, like we'll talk about semi-supervised, but I want to talk about just these 3 big categories. So supervised learning is kind of the classic case where we have examples of labeled input data and we train a model to try to predict the labels. So for example, in our housing example, the input data might be this house has 2,000 square feet, 2 bathrooms, and 2 bedrooms. And the output is how much should this house sell for, right? So our model is going to take that input and try to predict an output. Unsupervised learning is a little bit different. It's where you don't actually have labels and you're not actually telling the AI, oh, this is exactly what I want you to tell me, but you kind of let it learn structure in data by itself. The classic example we use is you have a bunch of customers and you're trying to put them into clusters, right? So you have all this data on your customers and you don't only have labels, but you want to learn, like maybe I have my soccer moms and my Karens and my Bettys or whatever. And these are my big categories of customers. And so our model could actually tell us, hey, here is some underlying structure here. And finally, reinforcement learning is generally this category where we have a model that is able to test itself out, usually in some kind of simulated environment. So for example, you can make a model that plays chess, and you can force that model to play chess against itself, and then really quickly it can learn from that experience. So those are our 3 big categories, and you can talk about AI ethics in all 3 of these categories, but we're really going to be zooming into that first category of supervised learning, where we are trying to predict something and we have some input data and we have some output label. So I want you to keep that idea of we have input data and we have an output label top of mind. Let's see, Mason Montana asked, why am I wearing a flower crown? I think the reason is because it brings me joy, and Global Hack Week also brings me joy, and so we're putting more joy on the joy that we already had. That's, I think, the best answer I'm going to be able to give. Fancy Appleby said, I like playing around with ML and TensorFlow and some weird data sets. I guess you're like an old pro at Global. Like you've been to a lot of Global Hack Week AI tracks, so that totally scans that you're actually into it. Thank you. Flowers are nice. You don't need a reason. Okay. So, Fancy Appleby said, what does ChatGPT run on? I'm going to guess this is like in the context of, oh, is this supervised learning or unsupervised or reinforcement? Or like, what is the input data? We could get into this. I think actually other sessions are diving into ChatGPT, so I will try to not go too deep on it. I also, okay, I'm going to spill a little bit of tea. So I think it's already known that so I work at Google and there's going to be a big presentation on AI things on Wednesday, I think. And I got an internal email about like, hey, here's what we're going to show. And I have no clue what in that internal email I'm allowed to talk about. And so I'm just going to try to stay a decent bit away from large language models because I don't want to say something that I'm not supposed to say. Okay, so we have these 3 cases: supervised learning, unsupervised learning, and reinforcement learning. And we're going to dive into supervised learning, where we have examples, and we're going to try to get our model to learn from these examples. So that is what I guess I should note that is machine learning. And AI and machine learning, we often use kind of interchangeably. There is a distinction which we can go into if you want, if you can ask a question about that. But we're kind of going to use those terms interchangeably. And so that's what AI is. Well, what are AI ethics? So something I actually am going to borrow here is Google has a set of AI principles that I think are actually really good. And they're what I actually use at work when I'm doing a sort of AI fairness testing. And so I'm going to drop that in the chat. So this is, and maybe actually I will just, to make this a more visual medium, I will pop it over here. And so we have, it's pretty small. Google has formulated a couple big principles for using AI to do things, right? I guess is the high level thing. We have 7 sort of imperatives, and then we also have applications we will not pursue. But so we're really going to focus on the first 2. I think all these are actually pretty good, but I think most of them are little things that, things that sort of dangle onto. Pardon me for moving my Colab notebook away. Things that we are going to attach most of our other things onto. So the first one is be socially beneficial. What does that mean? Well, you can read this blurb. I don't have it memorized or anything, but this is basically coming from what we call a consequentialist tradition. So we're going to get a little bit into philosophy here. If we have any, actually, if you're a philosophy nerd, say something in the chat. Say, yes, I'm a philosophy nerd, because we're going to go there. So being socially beneficial is an idea rooted in what I would call a consequentialist tradition. This basically just means that we want our actions to have a real positive impact on those around us. And I really like consequentialism because it gives you a really good framework for looking at these problems. But it does only take us so far. So a classic example that people throw out when you say, hey, I'm a consequentialist, or a utilitarian is another word that people use. Like, I want to be socially beneficial. Right? Yes, we have a philosophy nerd. Thank you for making yourself known. Wombo Combo, also a philosophy nerd. So if you say, oh, I'm a utilitarian, someone will say, but what about this example? And the example they'll use is say you have 4, I'm gonna make my face big again. Say you have 4 people in the hospital. They were all really, really great people. They're all saints, but they all have one organ that is failing vitally, right? And they will die unless they get a transplant. And then you have this other random dude who is honestly a total jerk. Everybody hates him. And he has 4 healthy organs that would actually be able to, if they were donated, save those 4 really, really nice people's lives, right? And you do the math, and you're like, well, this guy isn't going to donate them. But if we just took this dude and murdered him and harvested his organs, we could save 4 other lives, right? And they'll say, hey, if you are into consequentialism, you believe that you should randomly kidnap that person and harvest all their organs, right? And utilitarians will have different answers for why that's not true. But it is one of these limitations, is that utilitarianism, often we have a sense that it doesn't capture everything. I mean, we could turn this into just total philosophy nerd hour, but I'm gonna try to not go too down this rabbit hole. So consequentialism says you should try to do the best thing for the greatest number of people, or you should try to be socially beneficial. And in many cases, this is a really useful sort of anchor, but there are also limitations. So one of the other big pillars as like an answer to utilitarianism is called deontology. Lots of big words, but deontology basically means that you have specific duties to do things that are basically always things you need to do. And we can get deep into this, but the idea is that you should, just with your intellect, just with reason, be able to establish the rules that you should live your life by. So one of the classic examples that we use is should you lie, right? Is lying morally good? And the way you work through this for a deontologist is, hey, if I'm trying to lie, I'm trying to make somebody else believe incorrect things, right? And if that's my goal, my strategy is lying. Well, what happens if everybody does that thing? Well, if everybody pursues that strategy of lying, then what's going to happen is nobody will trust anybody. And if I then try to lie to you to make you believe something false, it won't actually work, because you are not going to trust me, because everybody lies, right? And so we can identify that lying is wrong just by kind of gaming out what would happen if everybody did it. And so this is sort of like one of, we get into the history, and Immanuel Kant, this is one of his categorical imperatives, right? Is that, if you can't universalize it, then it's not a moral thing to do. And so one of the general rules that we often agree on is this idea of fairness. We want to treat people fairly. Tomorrow we're going to do a deep dive into what do we mean when we say something is fair. We're going to do a Kahoot, and it's going to be a great time. But that is really the second AI principle Google uses, is avoiding creating or reinforcing unfair biases or unfair bias. And this is another sort of pillar that we're going to look at. So those are, utilitarianism and deontology. That's kind of like regular ethics. But what does it mean when we talk about AI ethics? How is that different? Oh yes, The Good Place. I love The Good Place. I think it is a really, really good show. Good Place, as I understand it, sort of like the philosophical core there is kind of contractualism, which is, I think, a really, really interesting branch of ethical theory. That, you know what, like next Global Hack Week, we're just going to do just philosophy, totally unrelated to tech. We'll see if Mary will let me do that. I think she might. So that's regular ethics, but what about AI ethics? So when normally when we talk about regular ethics, we're talking about, is it good for me to do a thing? Am I moral if I take this action? But when we create an AI, we're not always the one making a decision. The AI is making a decision, right? And the AI can hurt people basically in two different ways. The one way is the AI can hurt people even if it's doing exactly what we want it to, or the AI can hurt people because it's not doing exactly what we want it to. And I want to throw out two examples. So one is like writing an AI that runs on a drone that kills people, right? Now, even if you do your job perfectly as a machine learning engineer, people still die. We can have a separate conversation about whether or not like killing people is good or bad. But the point is that that's a conversation that's just regular ethics, right? Like, is killing people good or bad? And I would generally say, try not to do machine learning that you know is going to hurt people, even if you do it perfectly. So that's like regular ethics. But then there's this case where what if the model doesn't do what we want it to, and that hurts someone? And the example that I'll throw out here, I know we're doing like a lot of sort of case studies and examples because that's a lot of what like ethics and philosophy is, right? So if we built a model that is going to screen people for cancer, right? Like you give that model your X-ray and they tell you, you do have cancer or you don't. Our goal is to just like 100% help people, right? Knowing if you have cancer is like a thing that helps you get good care. But if our model doesn't do the right thing, even though we're trying to get it to be 100% accurate, occasionally it messes up. And when it messes up, it can hurt people, right? And so this then becomes a matter of AI ethics. It's not me hurting someone or trying to hurt someone, but it is a model that I made is now doing something that actually is making somebody else's life worse. So now I want to dive into the main event. I know I've kind of been vamping and talking about philosophy and ethics, which I guess is what you're here for. Let me know in the chat if any of that like is confusing. I think it's going to make a lot more sense when we kind of see these things in context, which is why I'm pumped to move on to our main event, which is a sort of a classic case study in AI ethics, which is that of mortgage approval. So in this scenario, really for the next 3 sessions, we're going to pretend like we work at a bank and our manager has asked us to write a machine learning algorithm to approve applicants for loans, right? So I never want to assume that folks know things about the world, but I also don't want to be insulting. Like I think folks know what like an interest rate is, you know. It's like, hey, I asked the bank for a lot of money and every month I pay the bank back some extra money. And by the end of it, I'm going to pay the bank back more money than I borrowed. And that's interest. We know what loans are. So our manager wants us to basically write an algorithm that will tell us, should I give a loan to this applicant, right? This person that wants a loan. And so we have data. The bank will give us demographic data, demographic information like their race and zip code, and also their credit score. Credit score is this number that usually ranges between 300 and 850. And if you have a really high one, it means you're really good at paying back your debt. And if you have a really low one, it can mean that you are not good at paying back your debt, for example. And importantly, because this data comes from the past, we actually already know if a person defaults on any loan following like the time that our data is from. So basically, we can know if a person in the past ended up paying off their loan or not. And so our boss wants us to predict for a new applicant in the future, based on all this information, will they default on a loan? Because if they do, then we probably shouldn't give them a loan. But if they're not going to default on that loan, then we should give them a loan. That's kind of our basic problem statement. Does that feel chill to everyone? If so, we will dive in and actually start poking at some bits and bytes. So I'll pause for a second and take a drink of water. And if anything about that premise doesn't make sense, let me know. But we'll kind of see what our actual data looks like. Okay. So I'm going to ask everybody to go to collab.research.google.com. If you have done a Global Hack Week with me before, you know all about this. You know what this whole deal is. But this is a really, really common tool that machine learning engineers use. I'll clear up. Colab is Google's version of a thing called Jupyter Notebook. Both of those things are totally fine. They work pretty similarly. The benefit of Colab is it's in your browser, and all of us will see the exact same thing. So if you pull up collab.research.google.com, let's put it up there, and you click New Notebook right here, you will get a fun little sandbox to play around with machine learning and with Python in general. So Python is our language of choice here. It's pretty easy to learn, and it's pretty expressive. And it is notably, I think, the most popular language for machine learning engineers to build machine learning and AI models with. And so what we can do is we have a bunch of these little blocks right here. These are called cells. And we can type something. So for example, in Python, we can print something out. We can say, hello. And when you click that play button, or you can hit Shift-Enter, and it will run it for you. The first command you run will take a second. It'll say connecting up here. But after a second, once it connects to a virtual machine somewhere, it'll actually run your code. Trust me, it does not take this long every time you run a command. Also, this will be faster if you're running locally as well. Sweet. So we said print hello, and it said hello. We can also do basic things like 1 + 2. And wouldn't you know, it gave us 3. Incredible. We can do, 2 to the power of 4 if we want. 16. Incredible. I'm not going to do a deep dive into Python. Often I'll start these tracks with, let's learn Python. Because we have a lot to talk about, if there's any Python that is unintuitive or that you're not sure about, totally ask me in the chat and we will talk about it. But otherwise, I'm going to kind of depend on most of this stuff being self-explanatory. And yeah, we'll walk through anything that's not. Let's see, Control-Enter, so I get a new cell. Oh, Control-Enter, I do Shift-Enter and I get a new cell. This Control-Enter, this might be, actually, do I? Yeah, I think this might be a Mac key bindings versus Windows key bindings, potentially. I don't know. Okay, radical. Oh, I also want to put out a quick warning. So I think this has been one of the hardest Global Hack Weeks for me personally to plan out, because there's kind of an easy template for all the other machine learning projects we do. We get our data set and we build a model and we build a better model and then we test it and it's great. But AI ethics is such an open field that it can be kind of hard to piece things together. So what does this mean for you? I think that the big thing is that there are, as we go through, especially today and tomorrow, there are probably going to be some obvious things that I do, and you'll be like, wait, Will, why are you doing that? That's obviously unethical. And the answer is, well, yes, I'm kind of setting up the situation so we can evaluate, why might this be problematic? So if you raise those questions, that's actually great. Totally ask the questions about hey, isn't this bad that we're doing this? And probably I will say, interesting question. We will get to that probably later. Thank you for the links there. Oh, also, if you want to just follow along, I will share a link to this. Copy link. Boom. So you can actually pull up the code that I am writing in real time. And if you want to copy and paste it and play around with it, you are more than welcome to do that. Okay, so let's actually get our hands on some data. So I'm going to copy a URL to a GitHub repository, which is just a convenient way to store a little bit of data and a little bit of code. And if you run that, it will download all that data to our local workspace. And if you come over here, you can see, yes, we now have some data. So we have loanapplications.csv. Incredible. Now, the next thing we're going to do is we're going to import a library called pandas. And we'll call that PD. So now instead of typing out pandas every time we want to use pandas, we can just say PD. And this is a really helpful library that lets us interact with data in Python almost as if it were a spreadsheet, which hopefully this will be a little bit clearer in a second. So we can say pd.readcsv, and this will read in our comma-separated value list from that we just downloaded here. Oh, pardon me. And we should be able to, if we go over here, we can see where it is. So we can just type Global Hack Week 2023-02/loan applications.csv. And then this is going to output that kind of spreadsheet object for us. It's called a data frame. And so we can store that in a variable called df. So that'll read it in for us. And then we can use this handy dandy command called df.head, or just your data frame.head. And this will give us basically a little summary of what our data looks like. It'll give us the first 5 lines of our data set. So you can see, kind of like I mentioned in our little problem statement, we have some demographic information, like race and zip code. We have their credit score. And then we have this column called will default. So this means, in the past, did this person who had this profile, did they go on to actually default on a loan or not pay it back, right? As this is similar to what you might actually get in a loan application. You'd probably get additional data as well, but we're kind of keeping this simple so we can focus on some of the ethical issues. So one thing we can do as well is we can select individual columns with square brackets. So we'll say df again, where we're storing our data. We can put some square brackets, and we can ask for a specific column. So for example, this column is called race. And so we can hit that and run that, and we get our entire thing of all the race data. So we have 5,030 rows, and all of these have different races in them. Let's see. It's saying access to open the notebook you shared. Let me see. Oh, thank you for mentioning that. Anybody can, we'll say anybody can view. Boom. Mad props to Daylovers, to Dayloves, for asking or mentioning that it was shut down. So now you should actually be able to go in and mess around and copy code that I'm writing if you want to. So this gives us a single column. We can also say, I'll try to keep all the lines of code still there. We can say df.columns, and this will actually give us a list of all of our columns. So our columns are race, credit score, zip code, and will default. Right on. So now we can use a loop in Python. We can wrap this in a loop in Python. So in Python, the basic way to write a loop is you say for variable in list or in iterable, and then you type your code down here. And so we can say for column in df.columns. And for starters, we can just try printing the column to make sure this is doing what we want it to do. Okay, it prints out our column names. But now we can use a function that Pandas has called value counts. So we can instead say df column. So this now selects the column, and then we can say dot value counts. And this will actually give us a little bit of a summary of how many different values are in our, like for example, what different races are in our data set. So we can run this, and so we see, okay, actually let's also just print out the, let's print the column name. And then we can print a blank line here. Okay, so we have race, and we have white, Asian, Hispanic, and black. Now you might say, this is one of those things that's like, wait, isn't this terrible? We might say, Will, isn't this like a laughably reductionistic view of sort of racial diversity in the world? And I would say, yeah, absolutely. It also is the kind of data that you might get in this kind of scenario. And so you should kind of learn how to think about it in a nuanced way. But yeah, so those are the races we get. We get credit scores, and you can see some credit scores repeat a lot. I don't know what it means that 666 is repeated 25 times. But a lot of our credit scores, like just one person has the credit score 413, right? So some credit scores are just more rare. So there aren't like big categories. We have zip codes. So it looks like we have 7 different zip codes. and they range from 71200 all the way up to 71207. And it looks like we have at least a couple hundred people in every zip code, but some zip codes are bigger than others. And then we have will default. And so it looks like most people won't default, but some people will. It looks like maybe a little bit less than, is that like a little bit less than a third of people? No, a little more than a third of people will default. Certainly less than half. Fancy Appleby asked, where did you get this set from? I will answer that at the end of this track. That is what I will do. Right on. But good question. Okay, so we looked at our data, but some of these are kind of hard to get a sense of, like especially credit score. Just looking at what common values are doesn't really tell us much. And so this is a great time to do some exploratory data analysis and actually try to visualize some of our data. So I'm going to use matplotlib. This is a very common Python plotting library. And so we can say import matplotlib.pyplot as PLT. So again, we're doing that thing where we sort of, what's the word? An alias. So we can just use PLT now. So a very, very sort of dumb basic example is we can say plt.plot, and we can give it some x values, and we could say 1, 2, 3, and we could give it some y values, and we could say 1, 4, 9, and oh no, got an unexpected argument x. What? How do you use plt.plot? Will it just infer if I just give it just the list? This one is one where I'm like, wait, I've used this thing like a million times. Okay, yeah, it's just going to infer our x values, or we're giving it y values. We're not even actually going to use the line function plotter because why would we? But what we will do is use a histogram. So I'm going to program out this histogram, and then we can dive into what it actually means and what we're looking at. So we can say plt.hist, and we can say df credit score. And because we're good data scientists, we're going to give our plot a little title. So we can say plt title, and we can say distribution of credit scores. Okay, cool. So you can see our lowest credit scores are 300. Our highest credit scores are a little bit over 100. If you want inside the histogram function, you can set a specific number of bins. So what if we said bins equals like 50? Cool, we get a little bit more information. I actually think that's maybe too much. Maybe we'll raise up to 40. But so what this is saying is basically not that many people have credit scores around 300, but tons of people have credit scores around like 700, for example. So some credit scores are more common than others, right? Another thing I want to do is actually just change the size of this graph to make it a little bit easier. We can also say plt.show. We'll just get rid of this data that gets spit out here. It should just make it a little bit cleaner. And then why don't we say plt.rc_params. So this can set parameters for like our whole environment, so I don't have to keep messing with this. And let's say figure.figsize, and let's set that equal to, we're going to give it like a width and a height. And I don't know, let's say 15 and 5. You don't really have to, this line right here, don't worry about it. It just makes our graph big. Oh, it's so big that it's causing problems. All right, cool. So this gives us just a sense of what our credit scores look like. Let me know if you have any questions about histograms. I know not everybody has taken like a stats class or a data visualization class, but I don't think it's too complicated. So this is our distribution of credit scores, but let's also get a look at the way that different variables interact with one another. And one way we can do this is by looking at a histogram per different attributes. So we could say for race in df race. So we're grabbing all our individual race values. We can do .unique just to get all of them once. And we can even wrap this in a sorted function. So this would just mean that we'll always get them in alphabetical order, which might make it just a little bit easier to look at. And let's say plt.title equals whatever our current race is. And then we can say plt.hist. And we will now we'll do something a little bit sneaky. Bear with me. So we want to basically get all of the data just when our race equals this current race, right? So what we can say, and actually I'll maybe just show this to you before because it's a little bit more complicated. So one thing we can do is we can say df race, right? That just gives us the column. We can also say when df race equals, say, white. And this will just give us basically a series of, hey, this row does have this this particular value, and this other row doesn't, right? So our first row, the race is not white. In our second row, the race is white. Now what we can do is we can take this and we can actually feed it back in to our data frame, and we can use this as a filter. So this is basically, if you are familiar with SQL, this is basically saying select where race equals white, right? So this is a way of just getting all of the rows associated with a single race. And we can now plop this into our histogram, but instead of just white, we can say race. And let's say, I don't know, bins, what worked for us up here, bins equals 40. And we can run that puppy. Oh, right, we forgot lots of things. Type of value must be an instance of stir or bytes. Oh, okay, we forgot one very important thing. So this little expression right here, if we bring it back up here and run it again, it gives us literally our entire data frame, but just particular rows. But if we want to just get credit score, for example, we can run that. And so now we just have all the credit scores of, say, white folks, right? So let's copy this back into our loop down here. Also, let me know if there's ever code that I am sort of blocking out with my head. Let me know. Welcome, Yashwant. Good to have you here. Okay, so we are, and then we want to, inside our loop, say plt.show, because that will just actually render our graph for us. And honestly, these are a little bit too big, so I'm going to say, we can say plt.figure, and inside here say fig size. And let's say like 12 and 2. So I'm going to make them, they're still going to be wide, but they're going to be a little bit not as tall, so we can hopefully see multiple of them on one screen. Oh, that's not good at all. What's going on? Oh, we want to set our figure first. Also, this is not a graphing live stream, so like if you're just kind of following along for the graphing, that's totally fine. That is not the main event. Okay, cool. So we see our distribution for credit scores for Asian folks, our distribution for credit scores for Black folks, our distribution of scores for Hispanic folks, and our distribution of scores for white folks. So we can clearly see that there is a correlation between the credit scores you're likely to see and race, right? And there are like actually lots of reasons we might think that we see this, right? And this is actually a thing to think about the context in which you are getting this data can be really, really helpful for framing these discussions. And so we will dive a little bit deeper into this in the future. But suffice to say right now, let's log, oh, okay, we see different distributions of credit scores in different racial categories, right? So there's correlation. Now let's look at the relationship between zip codes and race as well. So we could do like a not a bar chart. Yeah, we could do a bar chart. So we'll use a different graphing function that's just very easy for this. So we could say pd.crosstab, and we'll pass in an index, and we'll say the index is df zip code. So this is basically just saying what are the different categories on the bottom of our bar chart. And then we'll say columns, and we'll just say df race. So we'll look at basically, are our neighborhoods really, really diverse, or do we see like patterns of racial segregation in our neighborhoods, right? And so we will say crosstab results. What's that? Is it bar plot, bar chart? What is a bar chart? And then we can just say, actually no, let's call this crosstab result. And then we can say dot plot dot bar. And this should look pretty for us. Boom, there we go. Okay. So what are we looking at here? Well, on the bottom, each of these categories are a zip code. So we have 71200, 71201, and so on and so forth. And then we can see basically a cluster of the number of people of different races in that zip code, just that we have in our data set, right? So for example, in 71200, we can see that it's the largest racial category is Asian folks, and then after that we have white folks, and then after that Black and Hispanic folks. And you can you can do this process for understanding each of these zip codes. But so the other big thing to see here is that yes, like the zip code that you live in does affect the or what's the right way to say this? That there is a correlation between zip code and race, right? That there are more folks of particular races in particular zip codes. Also not like crazy surprising. There are lots of different ways to think about this. There, of course, is like a history of racial segregation in the United States. There are things, that we can point to like redlining, and there are also just things that we can point to like affordable housing. We don't have to dive too deep into specifically why this is, but it's good to remember going forward that race and zip code are not totally unrelated quantities, right? They definitely are have a bearing on one another. Okay, so that looks legit. What about where we're kind of going through all of our columns and looking at relationships between them, right? So we started just by looking at just credit score, but then we looked about what about race and credit score? Okay, what about zip code and race? And so now to round us out, we could talk about zip code and credit score, right? That are those things related? And so we can copy actually our code up here, and we could paste it down here. And instead of going by race, we could say zip code. And to be cleaner, we could just paste all these things, but we'll still be looking at the credit score here, right? Cool, so we get lots of graphs. And it looks like, at least in most of them, you have lots of folks. There's actually maybe is a little bit. Let's get rid of this. There we go. It looks like in most zip codes, you have more folks in the sort of 600 to 800 credit score range, and you have some folks in the lower range. It's not true for every credit score. Honestly, I think that looking at 8 different histograms here is actually a little bit harder. So I want to try actually using a different visualization called a violin plot. I'm really inadvertently turning this into the let's try a bunch of different data visualizations stream, which I guess is fun. I'm gonna go and change this on Twitch. It's not the AI ethics stream, it's the data viz stream. Okay, drop something in the chat if you are familiar with violin plots and if you like violin plots. I think violin plots get a lot of hate, and sometimes it's warranted, but I think sometimes they actually can be really helpful. So we are going to use another library called Seaborn, and we'll import that as SNS. So we'll say sns.violinplot, and we can say data equals df. So this is just giving our violin plot all of our data. And we can say our x value is going to be zip code, and our y value is going to be credit score. Loves has no idea about violin plots. Well, you're about to learn. You're about to find out. Okay, so here are violin plots. So what are we looking at here? Basically, this is it's very similar to a box plot. So you have actually in here a little box. So this is where most of our data falls, is in the middle here. And these 2 little lines go out to basically say we also have data in this range. So looking at this, we can see there certainly is overlap, right? It's not like in one zip code, everybody has low credit scores, and in another zip code, everybody has high credit scores. But you can certainly see that there are differences, right? Like in 71200 over here, there are, there's this really big pronounced hump of folks that have credit scores around 700. 71201 is a lot more stretched out. We can compare that even over here to like 71207. That there are, like a lot of folks lower in the credit score range. So this is, let's see, brother, do we get swags watching them? Or, so I don't know if this is a question about swag drops. If it is, I'll repeat this, that at the end of the stream, I will drop a feedback form. And if you fill out all of my feedback forms, then I'm going to raffle off. Well, I'll pick 3 folks that have filled out all of the forms, and we'll do swag drops for them. It also actually behooves you to fill out the feedback form because you will get to pick a really silly challenge you get to pick a prompt for ChatGPT to use to give me a really silly challenge. Okay, cool. So this is a violin plot. The other thing that it tells us is that different zip codes totally have folks with different credit scores in them. And this shouldn't be surprising, right? We saw that credit score and race were correlated. We saw that race and credit and zip code were correlated. And so it kind of makes sense that credit score and zip code also have a relationship. But it looks like a lot less pronounced to me, right? There actually is just quite a lot of overlap. There are always some people that have higher credit scores, and there's kind of this long tail of some folks that have lower credit scores. Cool. So that's a violin plot. I actually kind of like this, and I want to look at this for credit score and race as well. We can do PLT title. Let's see, credit score. We'll call this credit score and zip code. So we get a cute little title. And sure, we'll do plt.show just so we get rid of the weirdness. And we can just copy this cell. Can you just make a duplicate of it? Is that this? No. Duplicate cell. Okay, go into that. It's just too much work, so I'm just going to copy and paste it. Great. So now instead of credit score and zip code, we can say credit score and race. And so instead of zip code, we can say race here, and it should give us a similar view. Cool. Okay. So a similar story that maybe is even a little bit easier to compare here. That we have sort of a lot more stretched out credit scores for Hispanic and Black folks, and for white and Asian folks, we see a much bigger sort of lump, sort of near the top and near higher credit scores. So I think the last thing that I want to look at is actually how credit score affects default rate, right? The one morning I have to say, so I mentioned that violin plots get a lot of hate. I think the reason that a lot of people don't like them is that if you don't have that much data, your violin plot will still make it look like a nice little smooth distribution. And that can just be basically lying, right? Like your violin plot can lie to you if you don't have that much data. We have tons of data here. Remember, we have I think 30,000 rows or something. No, not 30,000 rows. How many rows do we have? Scroll all the way back up to the top. We have 5,000 rows. So we have 5,000 different data points. That's plenty, and the violin plot is not really going to lie to us. Also interesting, some interesting little bumps in there. There's a little bump right here, a little bump over there, which is, I will say, curious. Okay, what's left? Oh yeah, so let's look at the final thing is actually whether or not someone defaulted, right? And so we want to actually look at what's the relationship between credit score and defaulting. Oh my goodness, it's Polar Void / Alvin. It's good to see you. Welcome to the stream. I'm so glad you're here. So the last relationships that I want to look at, well, not the last relationship. But another relationship I want to look at is the relationship between credit score and did someone default, right? In theory, a credit score should be a good predictor of whether or not you're going to default. That's the whole thing it's supposed to be, is if you have a high credit score, then you will be likely to pay your debts. And if you have a low credit score, you'll be unlikely to pay your debts. So let's look at that. And I'm on a violin plot kick. So let's keep the violin plot going. So here, now as the category, so the X value, we'll say will default. So we'll say credit score and defaulting. So if we really dug in, okay, that's interesting. If we really dug in, there probably would be actually a definition of that this data set says will default if someone defaulted on a category, on a bank account in the next 30 or 100 days or something, right? We just have will default. And so what we see is, hopefully something that kind of makes sense, is that credit score is a good predictor of whether or not you're going to default, but it's not a perfect predictor, right? Like something we could imagine trying to do is just drawing a line, like saying, hey, if you have a credit score above 600, you won't default. And if you have a credit score below 600, you will default, right? But it wouldn't be, and it might actually be okay, but it wouldn't be perfect, right? If you drew that line like right here, you would still cut off a lot of folks that wouldn't default, and you wouldn't give them loans, and you would also cut off a lot of folks that, or you would give loans to lots of folks that would default, right? It's not perfect. And this is, I think I want to anchor this back to our discussion about ethics a little bit. We'll get more into it later today and tomorrow. But if somebody is deserving of a loan, if somebody is, I don't like the word deserve, but if somebody ought to receive a loan because they would pay it back and we don't give one to them, that is a way of hurting someone, right? Like they are worse off because we are not giving them this loan. We could turn this into a conversation about like housing policy and like the fact that specifically in the U.S. this is like very not true in say Germany, but like specifically in the U.S. That most of their wealth is tied up in a home that they have purchased with the mortgage, right? And so not giving someone access to a mortgage, if they could pay it back, actually is in a very real way preventing them from building wealth, right? So when we say, oh, if we drew a line here and we said these people can get loans, these people can't, that is actually going to make some people worse off, right? And that's the thing to be sort of very conscious of. So it's pretty clear that folks with lower credit scores are more likely to default. Folks with higher credit scores are less likely to default, which is sort of good to keep in mind. But what does this look like by race? So we could maybe we do another bar plot. Where are our bar plots? Did I get rid of? Oh no, here's our bar plot. We can do a lot of copy pasta. So now, instead of looking at, and for what it's worth, like when you're starting a machine learning project like this, actually getting really familiar with your data is something that you probably should do. It's something you always should do, and something that you often will spend a lot of time on. I think it's actually something that historically, when we do Global Hack Week tracks, I don't do enough of it, right? I kind of I'm more likely to kind of dive into let's implement the algorithm. But this is a case where, especially when you are concerned, I just knocked off my flower crown. Whoop. Especially when you are concerned about potential fairness considerations, you want to be really familiar with your data. Okay, great. So we have this again, and instead of looking at zip code and race, what if we looked at will default and race? Cool. Okay, so we see basically there are lots of folks who won't default. There are lots of folks of all races who won't default. There are lots of folks of all races who will default. We do also see definitely overrepresentation in non-defaulters of Asian folks and white folks. We see a little bit of an underrepresentation in we see an overrepresentation of those folks in non-defaults, and we see an underrepresentation of Asian folks in the will default category, which is interesting. This is not a thing that we have to form any particular opinion about right now, but it's like, again, good to know what these relationships are in the specific data set that we have. Now, I think actually maybe it is a good time to start talking about like, okay, what does this data mean? Why do we think the data looks this way, right? We're going to get a little bit more into specific kinds of biases that our data sets can have. But obviously our data sets always come from the real world, and the real world is not perfect and has a lot of like bad factors about it. There are a lot of like things that are not great in the world. There's a lot of racism and sexism and homophobia, et cetera, et cetera. And our data is going to reflect that, right? Pretty inherently. So one thing that you might know just from being, say, familiar with U.S. history and sort of U.S. current events is that we know there's sort of like a wealth inequality by race in the U.S., right? That if you are, for example, a Hispanic person, you are less likely to have intergenerational wealth that you have inherited. You are less likely to X, Y, or Z. And this is something that we might have a sense of, but it might be useful to actually like pull up some stats here. So I know the census, U.S. Census wealth inequality by race. There actually should be some good. Oh, this looks good. Some good data to look at. Where are you? Okay, cool. Here we go. So if we zoom in, so this is I think a good example of the yes, like the census does things not weird, but it has four categories here. It has Asian, white, Hispanic, and Black. And we can totally see that there is sort of this bimodal distribution. There's this cluster. Asian folks and white folks tend to have a lot of this family wealth, and Hispanic folks and Black folks tend to not. And we can dive even deeper into like, well, why does that tend to be, right? And you have like lots of historical things to point to. You have immigration policy. You have like redlining and Jim Crow. These are all things that have historically impacted the ability of folks of different races to accumulate generational wealth. And we see that kind of showing up here, right? So we understand that there is this detail about the world that there is inequality in the world, and that is showing up in our data set. And it's really, really important to not say, no, I think my data is like good and my model should just do the thing my data says. You should actually like acknowledge, oh yes, there is a clear bias in the data that I'm receiving that reflects a bias that exists in the world, right? That is a good thing to sort of call out. What else do we want to look at? I think we've looked at most of the relationships that seem pretty relevant. You can go on and you can start looking. We've looked at sort of 2 variables at a time. You can do visualizations looking at 3 variables at a time. But I think we have a good sense of what things are related, and this fact that there is this sort of real world bias baked into our data set. So what now? We have done our sort of exploratory data analysis. And if you've done a machine learning workshop with me before, you know I love to, before we jump in and build sort of like the real model, I like trying to implement a model from scratch, right? What would we do if we couldn't import scikit-learn, if we couldn't import TensorFlow, what would we actually build? And so I want to, this is actually great. We're at our halfway point. I'm going to take a quick intermission and drink some water and run to the bathroom really quick. But we are going to build the most basic model that we can in sort of the second half here and try to make it better. And we're going to start by learning about accuracy and write our own accuracy function, and then move on to implement really what is a basic linear regression. Linear classification. Logistic classification. There are a lot of words that are all kind of the same thing, but we'll unpack them in a second. But thank you so much for hanging on. And I'm just gonna, I guess, go back to my head while I fill up my water and go to the bathroom. I'll be back in like 2 minutes. I'll be back in like 45 seconds. Okay, I'm back. Oh, hello. Was it 45 seconds? I'm not sure. I should put on as a little stopwatch whenever I leave. I don't know. It's on my wish list of me upping my streaming game, but like actually getting into the putting up a screen that says we'll be right back or whatever. Get you some little intermission music. Fancy Alphabet says probably less. I will take it. Alan says that was fast. I will also take that. Okay. So we're back at it. We talked some philosophy. We talked about our sort of AI principles of being socially beneficial and not reinforcing historical unfair bias. And we kind of rooted that in deontology and utilitarianism, which is just great. I love that I get to talk about deontology and utilitarianism on stream. It's incredible. And then we got our sort of problem statement of we're building this model to approve loan applications. And we did some exploratory data analysis to understand the basic relationships in our data. So returning to what we started on, which was what is machine learning? Well, it's something that we take in labeled data and we try to make predictions about what those labels would be, right? And so In this case, really our input data is all these details we have about folks. And our output data is, our output label is, will they default? Something that I do actually want to do before we get too involved here is I actually want to switch around what our output variable is. This might make a little bit more sense later. So right now, if we just look at our data frame, we have will default. And defaulting is kind of the negative case, right? And we will get into, when we start talking a little bit deeper about things like, we'll talk about confusion matrices and true false rates and true negative rates, true positive rates and true negative rates and different measures of fairness. And in all of these cases, it's really helpful if we have sort of like the prototypical kind of like positive case and the prototypical negative case. And for us approving them and giving them a loan is kind of the positive case, and them defaulting and us not giving them a loan is the negative case. And so I just want to switch this around, and we can do this by saying basically should approve. And we can say this is basically just BF will default equals false. So if they won't default, we're saying we should approve them. And really the thing that's helpful here is just to not have any double negatives, right? Because once you start layering on the double negatives, it's like, well, they won't default, so we will give them a loan. Just saying we should approve them, I think will make things a little bit easier to understand. Fancy Appleby says, I can't see Adam's messages. I can't see Adam's messages either. Can anybody see messages from Adam? I hope Adam pulls through. So how does this whole thing work? How does our computer actually learn how to get better at a task? Well, the first thing that we have to do is we have to tell the computer what being good at a task means, right? And this is actually, I think, a really deep, meaty question of defining an objective function. Like, what are we asking our computer to do? If you'll permit me one little sidetrack, there is this famous sort of thought experiment of why you need to be really careful picking your objective functions. And the example is if you created a really, really intelligent AI and you told the AI, hey, like you run a paperclip factory and you want that AI to help you optimize paperclip production, you might say, hey, AI, make the most number of paperclips you can, right? And the AI might think about it. It's like, okay, we gotta move the paperclip making machines around here, and we need to run the factory 24/7. And then we'll realize it's like, wait, we could make more paperclips if like we had a lot more paperclip factories. In fact, we could make more paperclips if the entire world was a paperclip factory. And if I want the entire world to be a paperclip factory, that means I have to take over the entire world to turn the entire world into a paperclip factory. And so that means I need to like kill the president of the United States or whatever, right? And so because you picked this objective function that wasn't exactly what you meant, you end up with these really, really bad sort of fallout results. It's kind of a silly example, but it is an anchoring example of why picking your objective function is really important. And so the first thing that we are going to pick, or that we're going to look at right now, is something called accuracy. Hopefully this will not be a confusing topic. If you have done any machine learning, it's probably familiar to you. Also, if you have ever taken a test, like in your life, you are like a multiple choice test, you are also familiar with it. In testing, the idea of accuracy is just how many questions were there and how many did you get right. You take the number you got right and you divide it by the total number of questions, and that's your accuracy. So we could define an accuracy function in Python. This is the first time we're writing a function, so bear with me. Ask questions if it's confusing. But we can say define get accuracy, and it'll accept two inputs. So instead of questions and answers, we'll have predictions and correct answers. And what we can do here, it's really quite simple. We'll say we want to return the sum of the times that our predictions equals our correct answers. So basically every time a prediction equals a correct answer, and we'll just divide that by the total number of predictions we made. This just says, how many times did your prediction equal your answer? And then divide that by your total number of predictions. So if we get all of our predictions correct, we'll get a 100%. If we get half of our predictions correct, we'll get a 50%, right? And so this is the objective function that we're picking. And then we'll talk about different trade-offs we can make and different ways that we'll use this in the future. Oh my goodness, thank you so much for warning me there. Yeah, the problem is it's like I go 2 months without streaming and then I forget to actually share my screen. Okay, so we have our get accuracy function. I could rerun through that if anybody has questions, because I know I wasn't sharing screen when I typed it out. But so we're accepting our predictions and our correct answers, and we're basically grading our test, right? We're seeing based on how many guesses did you make and how many of them were correct, right? So we can just test this out. If you have done one of these sessions before, you will probably be familiar with the library NumPy. And it is basically just we use them a lot in machine learning, but a way of having a nice collection of numbers. So we'll say import NumPy as NP. And so we can define some, let's say, correct answers. And we could, import NumPy. And we could say our correct answers are NP array. I mean, in this case, if we wanted to, let's say it's a multiple choice test. And so the answers are like A, B, C. Those are our correct answers. And then our predictions are, let's say NP array. And let's say we got all but one of them correct. So let's say we got A, B, let's say we got A again. So we have 3 of these correct and 1 of them incorrect. And we feed this to our get accuracy function. We pass in correct answers, or we pass in predictions, and then pass in correct answers. We should get correct answers, plural. Oh, and it should not be in a list. I'm really fat-fingering a lot of things today. Good, 75. So we basically got a 75% grade on these guesses, right? So I use letters to kind of make it seem like a multiple choice test. But in reality, we'll often think of the predictions as being 0s or 1s, right? So a 1 could be approved for a loan, and then a 0 could be don't approve for a loan. And so if instead we said approve, don't approve, we get the same result, right? We basically got 75% of our predictions correct. You missed a chance to write ABBA. It's so true. I actually was thinking, this kind of feels like a rhyme scheme or a Swedish pop band. There you go. So we have kind of played with our accuracy function. We've also swapped the direction. So now the thing we're trying to predict, or maybe an even better word, is not should approve, but is credit worthy. The credit worthy is just like, should this person get a loan based on their credit history, right? So the simplest model that I can think of, if we come back up to this thing, basically these are all the people we'd like to approve, and these are the people we'd like not to approve. And if we drew a line right here, you basically pick a threshold and say everybody above it gets a loan and everybody below it does not get a loan, right? And we could just pick a threshold and say that's our cutoff point. That's kind of the simplest model I can think of. And so the thing that we need our machine to learn for machine learning is what is the best possible threshold it could pick to do that cutoff, right? So let's see. I think we're going to dive in. We're gonna code this up from scratch, and it's going to be this is going to be probably the most like heavy coding we do all track, like this whole week, at least with me. This is probably the most coding we're going to do. So buckle in, and we are going to. I don't think it's actually going to end up being that complicated, but it'll be a good time. So we can let's basically just start with defining. Let's start with just defining. Well, if we had a threshold, what would we how would we actually make predictions, right? So let's say our threshold is, I'm just going to pick a random number, let's say 500, right? And so we can actually do our predictions Actually, let's write a predict function. That's what we'll do. Apologies, my thoughts are a little bit all over the place, but I do enjoy getting in and just saying, what if we had to actually write the algorithm from scratch? So let's say we'll define predict, and it will accept a credit score, and it will accept a threshold. And you know what it's going to do? It's literally just going to say return, or here, I'll write it this way. We'll say if credit score is greater than threshold, return true. So we're saying they are creditworthy. Otherwise, return false. Now, I could have written this in fewer letters or in fewer lines of code, but I like this is just very, very expressive. And we're basically just saying, we will give you a loan if your credit score is above a particular threshold, right? This is actually our algorithm. And the thing that we need to learn is what should our threshold be. So the way that we're going to do this, and I'm going to introduce a couple of machine learning concepts, is we're going to basically try out our algorithm at lots of different thresholds, and we're going to try to narrow in on what the best threshold would be. And we're going to do this in a giant loop. So the thing we can do is we can pick a number of steps. So we'll say steps, let's say 20. So we're going to go through 20 of these steps of basically testing out a particular number and seeing which way we'd have to move it in order to improve it. And so basically we'll try out with a given threshold. And if we get a better accuracy when we move it up, we'll move it up. And if we get a better accuracy when we move it down, we'll move it down. And we'll keep repeating that process until we arrive at what is basically one of the best thresholds we could set. So let's start a threshold. We'll start a threshold at basically the lowest it could possibly be, which is 300. We're also going to define some additional variables. So usually in machine learning, we use capital X to mean our input data and lowercase y to be our output data. We could go into this. It's mostly just mathy things, right? X is often your input, y is often your output. But we will say X is just equal to our credit score. So the only input we're using is credit score. And the only output we're looking for is creditworthy. And so we're going to start this off by making a prediction, right? So we will say initial predictions is equal to predict, because we already have our predict function, and we'll just pass in our x and y. So we're starting out by just saying, hey, what if this was our, not x and y. We'll throw in our x and our threshold. And so we're going to do a line of predictions of saying, hey, what if our threshold was 300? What would our predictions be? And we'll just run our predict function on all of our data. So we'll get our initial predictions, and then we'll calculate our accuracy. So we can say get accuracy, and we'll pass in what does accuracy ask for? Well, it asks for our predictions and our correct answers. So we'll pass in initial predictions, and then we'll also pass in y is our set of sort of like correct answers here. Okay, does all of this make sense? We're starting off and we're getting a set of initial predictions based on our input data and a threshold that we just picked a random starting number. And then we'll get our accuracy from our get accuracy function. Alvin asked, how will that work? So maybe one thing just to illustrate is we can print out our accuracy at the end. So this is just with using a dumb threshold that we picked randomly. It's like the minimum value. We're going to use our algorithm to predict should we give these people loans, and then we'll calculate our accuracy based on those initial predictions we generated. Now, to be clear, this should be very, very bad. In fact, I think it should literally have a 0% accuracy, right? Oh, okay. We got an issue. What is our issue? In initial predictions, truth value of the series is ambiguous. Okay. I think actually what we do want to do, I tried to get fancy and it's not having it. We'll just actually return is credit score greater than threshold. And that'll be fine. Okay. I see actually what happened. Yes, yeah, no, when you get into vectors, you gotta stay in vectors. And sometimes your brain tries to trick you and think that you're not working with vectors, but you are. Okay, so or actually is 62%. What's going on here? Well, okay, so we set our threshold to 0, which basically just means we are approving everyone, right? Everybody gets a loan because everybody is above our threshold of 0, right? Or above our threshold of 300. But what this means is that everybody who deserves a loan, we got correct, and everybody who doesn't deserve a loan, we got incorrect, right? And so just by saying give everyone a loan, we got 62%, which is not that bad, right? Like not the worst. But obviously, and this is all we had to do. Like, the bank would not have hired us to write them an ML algorithm, right? It's very easy to just say, just give everybody money. Doesn't actually improve the way your bank functions. Okay, so another thing I want to define is, what will we say? Okay, well, we'll define something called a learning rate in a second. So we got our first initial accuracy, but now we're going to write a loop. So we'll say for I in range steps. And so inside this loop, for starters, I'll just say print trying to improve our threshold for round, and we'll pass in I, and we'll just put an F at the beginning there. And so this will just say, okay, we're running through 20 rounds of trying to improve our threshold. And the thing I want to try is we're basically just going to say, well, what would happen if we increased the threshold, and what would happen if we decreased the threshold? And if one of those is better, let's change our threshold to that, right? And so we have to pick an amount to change that's different. So let's just try, let's say higher threshold is equal to threshold plus 100. And so now we have a higher threshold to try out. If you obfuscate the code enough, the bank will believe you. I dig it. So we have a higher threshold to try out, and we're just going to test it out and see if it works, right? And we know how to get predictions. We can actually just copy our initial code to get predictions, and we'll say higher threshold predictions. And we'll pass in our higher threshold. And we'll get our higher threshold accuracy by passing in our higher threshold predictions. So just to recap on what we're doing here is we're saying, okay, what if I increased the threshold by 100? What predictions would I make? And then what would my accuracy be if I made those predictions? So we're just playing this game of what if and seeing if our predictions would be better if we did things a little bit different in this way. So what do we want to do? We can say if our higher threshold accuracy is greater than our original accuracy, then what do we want to do? We could say increasing threshold, and we can say our new accuracy is equal to our higher threshold accuracy, and our threshold is equal to our higher threshold. So we're just updating. We're saying our higher threshold was better, and so that is now what we're actually going to use as our threshold. We ran the numbers, and it actually works better, and so that's what we're going with. Do we have any questions about what's going on here? So we say, hey, we're gonna take 20 steps, and every time we run this, we're going to see, would things be better if we had a slightly higher threshold? And we'll calculate, and if they are better, then we'll update our threshold to that. Cool. And actually, let's add a few more logging statements. I'm gonna get rid of this, but we'll say, let's print. We'll say if our, let's move it down here. If our threshold was, we'll pass in higher threshold, then our accuracy would be, we'll pass in our higher threshold accuracy. And if we run this, we should have some machine learning happen. Incredible. Okay, so what do we see happen? So we say if our threshold was 400, then our accuracy would be 0.7. And we know that's better than our original accuracy of what it was like 62. So we say increasing threshold. Then we say if our threshold was 500, then our accuracy would be 79%, increasing our threshold. Then we say if our threshold was 600, then our accuracy would be 80%, increasing threshold. And then we say if our threshold was 700, then our accuracy would be 0.64. So we raised our threshold too much, and it started getting bad, right? Okay, Alvin, I'm going to say I did not see this comment when I did it, but great minds think alike, and that's where I'm at, my guy. So then we have a bunch of this that's like really, this right here is wasted compute cycles, right? There's no point in this happening. So something that we can say is basically if we didn't update our threshold, then we should like break out of our loop. But another thing, actually, no, yeah, this is good. This is good. So at the very beginning, we can take we can save a snapshot of our original threshold. And at the very end, after we do all of our compute, we can say if original threshold is equal to threshold, basically saying if our threshold didn't change in this entire loop, then we'll say didn't update threshold finishing learning. So now, oh yeah, we actually have to break. We can hit break, and this will break us out of the loop, and it'll say, hey, don't run your loop anymore, right? Cool. So now we've saved a lot of compute resources by not running our loop extra times, right? And so we can see we keep increasing, and then when we get to 700, it says if our threshold was 700, we would get worse accuracy of 64%. So we're done, we're finishing learning. And if at the very end, if we just print out our threshold, we get 600, right? Because that was the last number that we saw that was still actually good for us. And so now the important thing is we have actually done, like pat yourself on the back, we did a machine learning, right? Like our computer actually got better at things. And what we can now do is our original predict function, we can pass in our threshold. And now we can put any credit score in here, and we can actually get a result. We can get a prediction of should we give this person a loan, right? Basically saying, will this person default? So, well, what if a person has a credit score of 550? And of course, we get false. We say, no, don't give them a loan. Okay, what if we pass in a credit score of 700? Do they get a loan? Does that person get a loan? Yes, give that person a loan. This is true. So we now actually have the ability to make new predictions on credit scores we've never seen before. Let's see, Evan said, how often are floating point inaccuracies an issue when creating a model? This is a good question. And I think the actual answer is way less of a problem in machine learning than a lot of other fields. I think floating point inaccuracies can cause lots of issues in cybersecurity. They can cause lots of issues in financial math. We don't often think of them causing that many issues in machine learning. Technically, the one actual problem, y'all always get me on the best tangents. There was this thing called the vanishing gradient. And it only pops up in more complex neural network models, which we can talk more about if you're interested. And you might be familiar with this. But the idea is if you have like a really, really big brain, right here, our brain is basically like one mathematical operation big, right? It's just, if I set this threshold, did we get the answer right or wrong, right? And you just can update that immediately. But with these big models, you have lots of dominoes that fall. And basically, this is Alvin, of course, I know you know these things, but, sharing with the class. And we have to sort of like, the last domino to fall has to tell the domino before it if it got the answer right or wrong. And the domino before that has to tell the domino before it if it got the answer right and wrong. And you have to do this thing called backpropagation, right? And the thing that actually, the one case where I know that floating point numbers can cause issues in this, I mean, it's not exactly just floating point inaccuracies, but the thing that will happen is because the numbers that you are multiplying back in your backpropagation can get so small that they get close enough to zero that your computer is like, yes, this is zero. And this is called the vanishing gradient problem. And it is when you have basically basically instead of just saying yes or no, you say yes, but just a little bit yes, or no, but just a little bit no, and it gets close enough to 0 that you're actually unable to like usefully do math on that. That's the only case where I can think that floating point inaccuracies actually cause problems. But maybe there are others. I don't know if anybody else has ideas. So we have created a machine learning algorithm. You pat yourself on the back. This is great. We have done learning. But how can we make this better? If we're just playing around, so one thing we did is we have this learning rate right here, right? And this is basically how much we're changing our answer to actually test things out. And obviously this means, because we made it 100, it means we're only ever going to get a threshold that is 100, right? So one thing we could do is we could just reduce this to like 50, right? In fact, actually, let's create a variable called learning rate. This is how much are we changing our guess every single time. And let's say that's 50. Cool. Put that in there. And if we run this, oh wait, actually, I should have tested this both ways. So we actually still get a threshold of 600. In fact, this is great. We can model some good machine learning science here. Let's actually keep a little lab notebook. So with a learning rate of, what do we say? With a learning rate of 100, our threshold, you can say threshold was 600, and our accuracy achieved was, we can just copy 80.48. How about that? This is like our first experiment, right? And we reduced our learning rate to 50, and we actually got the exact same results, right? We still landed at 600 as a good limit, and we still got the same accuracy. Okay, what if we went even smaller? What if we said our learning rate was 25? We still get 600. Okay, this is a little bit funny. Okay, we could change to a smaller number. What if we said 5? What happens? Okay, so this is actually great. So what happens when we set our learning rate to 5 is we actually end up with a worse result just because we didn't have enough iterations, right? So we could, instead of just saying 20 steps, we could say 100 steps, right? And so it'll keep running. And okay, we get a different number. We get 535, right? So when we set a learning rate of 5, we get a threshold of 535, and our accuracy is, oh wait, actually, our threshold is 530, isn't it? Our threshold is 530, and our accuracy is actually higher, 81.17%. Boom. This is also something that you get used to when you do enough machine learning, is that like, oh, being able to tweak a parameter and seeing an increase of like 1% accuracy, that's great. That might feel like, what? We changed our learning rate and we only increased by 1%, but like, no, we're super psyched about that. We're thrilled, right? Remember the first original dumb model was getting 60%, 62%. Now we're up to 81%. And that's an improvement, right? One thing that we might be concerned about is, hey, this loop is really, really long, right? And how many iterations did we have to go through? Well, maybe not all 100, but that's a lot. And right now, our model is really, really simple, so it doesn't actually take, you can see our RAM and disk up here, and we're not really using that much of it. But as you build bigger and more complex models, the longer it takes to train, it can actually be really, really like expensive and prohibitive just because it takes a long time to train. And there's something that you will often try to be clever about, is doing something where you actually change your learning rate over time. We're getting into sort of like machine learning 101, the basics of you have a learning rate, and instead of just saying, when we set our learning rate really, really high, we never got really to like quite the right place in the middle. But when we set our learning rate really, really low, it just took a long time to get to the best answer, even though we got a better answer out of it. So something that you can do is you can play around and you can say, well, what if we said our learning rate is like 20, but every time we take a step, like at the end of every loop, we actually adjust our learning rate to be like maybe I don't know, what do we say, like 95% of the original value. I don't know, maybe this of course gets into the tweaking, right? So every loop we go through, we're going to make our learning rate a little bit smaller. Let's see what happens. So in this case, actually, I want to comment this out, and I actually want to just keep track of our total number of steps. So we can print at the very end. We can print I. We can say in I total steps. Because ideally we want, oh yeah, I wrote a bug. Ideally we want to get a really, really good answer, and we want to get that answer really fast, right? Okay, so here was, this is with 20. Let's say if we made our learning rate 100, that's where we started, we did 3 steps, right? So it took 3 steps. We did a learning rate of 50. It took 5 steps, and we actually got the same result. 5 steps. And when we changed our learning rate to 5, we got a better result. It took us 46 steps, right? So we traded off. We got a little bit of a better result, but it took us more compute. And so then finally, I want to try this to see if we can actually improve. What if we said our initial learning rate is 20, but every time we take a step, we reduce our learning rate a little bit? And let's see what we get. Okay, we get what ends up being, I think, technically even better than our original score, and it only took us 21 steps. So this was learning rate of 20. Our threshold ended up being 563. 7, we'll say. Our accuracy was 81.8169. Nice. And it took us 21 steps. So we got an even better result with less compute resources, and that is totally a win. This is we're kind of just diving into, sort of basic classic machine learning. How do we make it learn a better set of parameters from the data as fast as possible? But I want to zoom out, and I just want to come back to this idea that we didn't have to tell the computer how to pick the right threshold. All we had to do was tell it how good a threshold was using our accuracy function, right? We decided what we wanted to optimize for. We wanted to optimize for accuracy, and our computer, just by throwing some compute and some data at it, generated for us a threshold that gives us the best accuracy, right? And sure, maybe it's not exactly, maybe 564 would be a little bit better, and you could keep tweaking with the parameters. But we've got an answer that is at least really dang close to the quote unquote correct answer in this scenario. And so I want to, I think, end on this idea that we picked a thing we wanted to optimize for, and our computer did the work for us. Do we have any other questions at this point? Because I think tonight we're going to leave it there, but I will, of course, do a little housekeeping. We will drop our let's see, our feedback form. Boom. So these, I will show you what the feedback form looks like. Boom. So I really, really appreciate hearing how fast this session felt for you. I'm always trying to get it to the right place where it's not boring, but it's also not like I'm just rushing past everything. So let me know if it was too fast or it was too slow. Also, let me know if you had a good time. If everybody's like, "Hey, Will, your sessions suck," I'll stop. It's fine. And then the big one is, so historically, I've always tried to do something silly for Global Hack Week. I have given myself a tattoo. It's temporary. I've dyed my hair. I have painted my face. But today, this time, I am going to have everybody give me a prompt to give to ChatGPT. and ChatGPT will then give me a recommendation of something silly to do. And then next time we will vote on all the silly things that ChatGPT tells me to do. I also have to credit, I don't know if anybody went to Nick Quinlan's session. I think he has already done a D&D with ChatGPT live stream. He gave me the idea to do this. So for example, I used the prompt, can you give me a silly task to do on stream involving ukulele? And ChatGPT said, play Mary Had a Little Lamb on the ukulele while standing on one foot and making animal noises for each chord, which I actually think is great. I'm going to include that one in the running so you can vote on that. But if you put a prompt there, I'll run it. And then also, if you have any other questions, you can let me know in here. But of course, remember, if you fill out this form and you fill out all the other ones, then you will be eligible for the swag drop raffle. Thank you all so much for coming. Fancy Appleby, thank you for the links, as always. Oh, and this is something that folks in the past have always asked me for is, hey, Will, I want to do something in between sessions to add to the learning, to go a little bit deeper. And so I now do, I'm going to throw some links at you. Not like deep reading or anything, but there are 2 good crash course philosophy videos on utilitarianism and deontology. I think they use, they might call it like, I think they just refer to a categorical imperative. I think they talk about deontology too, though. Thank you all so much for being here. It's been a joy as always. Next time, we will really actually get into, like this time we built the machine learning model. We'll actually kind of productionize it and make it a little bit more robust, but we'll actually get into the, hey, what is fairness? Hey, should we be concerned about particular things with the model that we have written, which I think is going to be just really freaking great and super valuable to all of us as machine learning practitioners. So thank you so much for being here, and I will see you all tomorrow. Happy hacking.